So let's finally then get to option pricing methods more generally. So what we've looked at so far is that this price process, or formerly a risk neutral actually price process, that this S, the stock price, is going to obey, that's going to define some future distribution, as we saw, of this underlying asset, this stock price. And if we know the distribution, so we saw with the geometric gradient motion that distribution is given by a log normal distribution. So if we know the distribution, then we can price actually derivatives on that underlying, on that asset, on that stock. So how can we do that? Well, sometimes it's possible actually to do this analytically, and precisely this BlackScholes formula was an example of that. So sometimes we can actually explicitly compute that expected value and then take the discounted value of that, so the present value of that. So that gave us this BlackScholes formula. But often that's actually not possible. So actually, apart from taking the expectation, actually sort of similar approach or related approach, this is solving a closely related partial differential equation. Often actually it's not possible to do this analytically, and we have to rely on numerical methods. So I'll briefly mention, I'll basically outline two different approaches to that numerical computation of option prices. So one is Monte Carlo simulation, and the other one, and actually the one that we'll use in this brief course, is using binomial, or rather actually trinomial trees. So we'll have a look at that briefly as well. So how do we compute discounted expected values? Well, again, with the geometric gradient motion, as the log of S, so the natural logarithm of S, is normally distributed. So that means if we know the payoff of at the maturity of the option, which can be anything. So for these exotic options, well, they can be very exotic payoffs as well. So let's just call this payoff some function f of the stock price at time t, at the maturity date. So if we know that, then we can actually compute the expected, we can compute the value of the derivative of this exotic option as the expected value of that payoff, and then discount this expected value E of this payoff f of st. We discount that with this discount factor e to the power minus rt. So that's going to be formally basically the value of the derivative. Well, sometimes this is easy to compute. So for a forward in particular, so we saw for a call or put, not that easy, but doable. You can get the BlackScholes equation. That's what Black and Scholes, after all, did. For some contracts, it's actually a lot easier. So for a forward contract that has an even simpler, or has much simpler actually, a payoff, namely is just the difference between the stock price at maturity minus the strike price, the exercise price. It can be positive or negative. So remember, a forward contract, you can gain or lose, so just a linear payoff essentially. So can we actually compute the value of a forward contract? Yes, we can, by going exactly through the same motions. What we do is we take the expectations of S minus K at the time equal to maturity, so capital T, and we discount that by this discount factor e to the power minus rt. So can we actually compute what the expected value is? Well, the expected value of k is of course k. The expected value of t under this risk neutral process, this risk neutral measure it's called, is just s but inflated with e to the power rt. So remember this, instead of having this growth rate mu, what we had to do, we had to exchange this with a growth rate equal to the interest rate to get something which is called risk neutrality. So this is something that we can compute. Just multiply this out, e to the minus rt times e to the plus rt, that's just 1. So this first factor gives us just a 0. The second factor gets minus e to the minus rt times k, so that's the second bit here. And this indeed, actually, if you do derivative course, you will recognize this as the value of a long forward contract. So this is something that we can do in some cases, in particular for this forward contract and for these European calls and puts. but that we cannot do for just any payout. So at some point it might get a little bit too hard, and what's also hard is actually, or almost impossible, is to do this analytically for an American style option in many cases. So the other approach to finding this value is turns out to be by solving some particular differential equation, a partial differential equation. So that relies basically on a correspondence or mathematical, or it's almost a mathematical correspondence between stochastic processes, so these random processes in time, and differential equations. So that turns out to be a relation, equivalence between these generalized Wiener processes, so these Brownian motions, and partial differential equations. And on the other side, the expected value of the payoff under this Wiener process, under this Brownian motion, and the solution to that equation. So in particular for this geometric Brownian motion, the related partial differential equation is what's called the BlackScholes partial differential equation for the value of some derivative. So this is actually an equation that holds for any European style derivative on some stock price S, which follows the geometric Brownian motion. So what we see here is the value of this option itself, the value of this derivative itself is called the V. Will be a function of S, but it will also be a function of time. Well, the interest rate times this value turns out to be under this particular differential equation equal to the derivative with respect to time of that object, and some combination of derivatives with respect to the stock price, partial derivatives with respect to the stock price of this value. And in particular, in order to find the value for a particular payoff at maturity, so a particular little f, which is the payoff at time capital T, as a function of what the stock price is at that maturity time, that will be the boundary condition basically for this partial differential equation. Well, solving partial differential equations is typically not easy. Again, often very hard actually. So most of the time actually we cannot solve these equations. So BlackScholes again could solve this equation, the BlackScholes partial differential equation, for the particular payoff of a call option or a put option, but for more general options this turns out to be hard. So how can we solve these equations approximately or in a numerical fashion? Well, we need actually some numerical approach so that you can make an approximation, numerical approximation, and we do this of course on a computer. So you can almost not do this by hand to any good approximation. So one way to do this, to solve these equations, is using something which is called Monte Carlo simulation. Basically what that amounts to is Monte Carlo simulation amounts to having lots and lots, as in 100,000 or a million random paths, drawing those random paths that stocks might follow according to this geometric Brownian motion in the future. And for each of these paths, you just compute the average discounted payoff. So you compute the payoff according to that particular path. So here you see every stock price starts today at 1. So there's a particular one of these random paths, and it turns out to grow pretty big after 250 days, namely to 2.5 almost. So this is just one path, and this is going to be a majority. Here we can compute what the payoff is. We do this for each of these 100,000 or a million different paths that you see here. Then we take the average value, and that's one way to compute essentially this expected value for the option. So that's Monte Carlo simulation. That's one approach to solving this expected value or this solution to this partial differential equation in a numerical fashion. So that's one thing that we could code on the computer. The other approach is using a so-called binomial tree. So a binomial tree means, well, let's look at the stock price, which again starts at our initial value. So I took the initial value to be just 1. And let's just now assume that starting from this initial value, the stock price might just move up with probability, some probability, I took a probability a half, or it might move down with probability a half. Well, in this particular case, if it moves up, it will reach a stock price equal to 1.5 in this picture. So with probability a half, the stock price moves up to 1.5, and with probability 1/2, this stock moves down and it gets smaller and it goes to the lower value of 0.5. Then one period after that, again, starting from where we are here, remember this was this Markov process, again, it's like we are flipping a coin again. The stock price might go up again, reaching perhaps 2.25, which is 1.5 squared. Well, that might again happen with a half if we flip our coin. But also, on the other hand, we might hit the tails if we flip our coin. And actually the second step might be downward, so it's halved. From 1.5 it goes to 0.75. Same ways down here. So after the first step, when the stock price was halved, after the second step we might get ahead if we flip our coin, so stock price goes up and we reach also this 0.75, but now through this alternative path. And with probability a half, you might have a second tail if you wish, so second downward movement, again having this value that we had before, going to 0.25. Now this is a very easy, transparent process that the stock might follow with these discrete steps. But imagine now that we make these discrete steps smaller and smaller, so that we make the time steps smaller, and we also make the steps in the increments or the decrements of the stock price, make these smaller. So instead of going from 1 to 1.5, all of a sudden, perhaps we go from 1 to 1.1. If you go up to 1 to 0.9, perhaps if you go down, and continue in that way. So the closer and closer you make these time steps, and also the changes in our stock price, the closer this whole tree. So we're building here a tree, if you wish, with different branches, starting from the root over here, some up branch, the down branch, the higher branch, and the lower branch. And some of these branches recombine again here, as in this particular point, or they might go further up or further down. So if we make this tree denser and denser, so closer and closer together, in the limit that we take these steps very small, this result of this tree of this motion, basically, that this S goes through in every different path of this tree, actually resembles this continuous time stochastic process. So what we can then do is use our computer to evaluate the probability of each and every of these paths. So here we just have 4 paths, 2 ups, an up and a down and an up, or a down and a down. And you can imagine that as we increase the number of steps and make them closer and closer together, well, the amount of numbers of steps and the amount of time steps is going to go up. Also, the number of paths are going up. But you can actually enumerate all those paths on our computer and actually compute the different values for the stock price along each of these different branches that we are following, and actually use those to compute the end value, the different probabilities essentially of the end values that we might have. So the probability in this simple tree here is, if you go up twice, well, what's the probability of that? Well, it's a half times a half, so a quarter. What's the probability of remaining in the middle? Well, there are 2 paths, so with probability 1/4, you might stay here but go there through the up-down trajectory. But also with probability 1/4, we might end up there by going first down and then again going up. In both cases, we end up at this middle node over here. And again, with probability 1/4, a half times a half, we might end up at this lower node here as LL. As we keep on expanding the number of time steps, obviously also this number of paths is going up. But with a computer, we can actually keep track of all those paths and compute the different probabilities with the different outcomes from this tree. So if you do that, then the value of the initial value of the derivative is going to be the sum of the different outcomes that we would have for the different end values that we might end up with, different endpoints of this tree, weighted by the probability of all the paths that end up at those different values. And that's what we're going to do in this binomial tree approach to pricing options. So to wrap up what we're going to do in our coding course, we'll follow this latter road. So we're going to use this tree. Well, in fact, we're not going to use this binomial tree. So binomial in the sense that there's always an up or a down, just two paths. So we're going to use a trinomial tree because that's going to be slightly easier to implement numerically. So that means there's three branches coming out of each node, up or middle or down. So that's what we're going to code in our Python program. And actually, we're going to extend this tree a little bit into a complete grid. And that's going to be actually, well, not something we have to worry about, but you can show that this is actually equivalent to solving this partial differential equation so this BlackScholes equation that I mentioned before, in a numerical fashion using an approximation which is known as the explicit finite difference method. So that's basically what we are coding in our course, in our Python course. So what we'll do first is in the course is we'll start doing this for European and for American plain vanilla options, so calls and puts. And then what you're going to do is to extend those pieces of code that we're creating there. You're going to extend those to also make them handle options with more exotic payoffs of your choice. So this is a little bit of the background that might be nice to know to see what the connection is basically with option pricing theory.